Hey everybody, Mr. Dow here again. Today I'm going to be talking about Chapter 5, which deals with probability, the study of randomness. One of the most common places to use probability is in Las Vegas or in Atlantic City or anywhere where you want to gamble. If you understand probability, maybe your chances at the tables will go up a little bit. The idea for you as a consumer is to go to Las Vegas, win big, and then stop playing. Every now and then Las Vegas is going to give out a big win on a jackpot, but for that specific casino they're going to be taking in so much more because they're there for the long haul. And since they're in for the long time, they're always going to be making money. The idea for you, just get in for the quick run, make some money, cash out, go home. And with probability, if I do something long enough, I should get similar results. If I flip the coin enough times, I should get an even amount of heads and tails if the coin is balanced. If I only flip the coin a few times, maybe I get more heads than I do tails. But in the long run, it should be a 50-50 split. Well, what's the long run? 10,000 flips? 20,000 flips? Well, I don't know. Sometimes I might get a probability of 20%, sometimes it might be 60%. But let's say 10,000 times, I should get around 50%. When dealing with probability, we're dealing with the concept of things being random. Random doesn't mean haphazard, though. It's what is happening in the long run. I see plenty of things that occur to me during the day that I might consider random because I don't see them that often. But maybe I'm just never in that exact same time, exact same spot often enough to see long-term regularity. Here's a very simple example of that concept. Another idea of this concept is if I went to California or to San Francisco, I might be involved in an earthquake. And I would think, man, that's random. I went all the way out there, and at one time I'm out there, there's an earthquake. Well, to me, it might be. The people that live there see earthquakes all the time. It's not really that random to them. Here is the definition of random. Now, probability does involve randomness. Here's your definition of probability. The idea here is the theoretical probability is what we would see in the long run or long series of repetitions. Probability must involve independence. Independence is when one outcome does not influence the next. For instance, if I roll a die and a 3 comes up, if I go to roll the die the second time, that doesn't mean a 3 is not going to come up, or a 3 is any more or less likely to come up. One event is not influencing the next. If I'm shooting baskets and I make 3 in a row, that doesn't mean I'm going to make the 4th, doesn't mean I'm going to miss. The 4th shot is independent of the first 3. A sample space. That would be the list of all possible outcomes. If I were to toss a coin, only one of two things can happen. I can toss it and get a flip of a heads or a tails. I would say S, to represent sample space, would equal H or T. If I were to roll a die, the sample space would be the outcome S equals the numbers 1, 2, 3, 4, 5, and 6. If I were to toss a coin and roll a die, the sample space for that situation is a little bit more involved. It would best be illustrated with a Venn diagram. Let's flip the coin first, then roll the die. I can either get a heads or a tails. From then, I can roll any of the numbers 1 through 6. I can roll a heads and then a 1. If I go to the end of the branches, I would get the combination H1. A heads and then a 2. End of the branch, I would get a combination of H2. All the way down to flip a coin, get a tails, roll the dice, get a 6, and have tail 6. The combination of H1, H2, all the way through to T6 would be my sample space. The multiplication principle is a principle that allows me to count how many ways can I do something. For instance, if I had 3 t-shirts and 4 pairs of jeans, if I multiply 3 times 4, I could say that I would have 12 outfits. The multiplication principle says the following. Next concept is the idea of replacement or without replacement. If I were drawing cards and I wanted to know the probability of drawing an ace, there's 4 aces in the deck out of 52 cards. The probability would be 4 out of 52. If I'm going to draw a second card, well, the probability of the next card being an ace depends on whether I put the original ace back in the deck and reshuffle, or I keep it out without replacing it and getting another ace. So am I putting the card back in, reshuffling, or setting that card aside? Replacement or without replacement. Here's another example. Put 10 numbers in a hat. Let's number them 0 through 9. I'm going to choose 3 with replacement. If these 10 numbers are on slips of paper, and let's say the first number I draw is a 5, well, there's 10 possible numbers I could have drawn for that 5. Using the multiplication principle, I could say 10 times, now for the second number, if I'm putting the 5 back in, I have 10 additional ways, times 10 for 1,000 3-digit numbers, as long as I'm putting the numbers back in the hat or replacing them. If I were not replacing the numbers, once I draw my first number, there's 10 ways to do that, and that number gets set aside. It does not get replaced back into the hat. Now there are only 9 numbers left to choose from. The multiplication principle says it would be 10 times 9 times 8, or 720 3-digit numbers. And that's pretty much it for the first section of probability.